Have you ever thought about learning not as just cramming your brain full of facts, but something more? What if it was more like skillfully reshaping the very map of your mind? Today, we're diving into a really cool idea that suggests just that, the topological theory of learning.
So, let's just throw out that old idea of learning as, stacking books on a shelf. I want you to picture this instead. All of your knowledge is a map. So what if learning is the art of redrawing that map to make room for new discoveries, all without losing your way?
And this is really the core of the whole thing. It views learning as the seamless expansion of what you already know. You're stretching your understanding to include new ideas, but, and this is the crucial part, without breaking the connections that hold it all together.
All right, so let's dig into the details. This new map of learning is actually built on some pretty elegant mathematical ideas that give us a fresh perspective on how our minds actually evolve.
Now, I know what you're thinking, math, but seriously, don't let that scare you off, because at its heart, it all boils down to two really simple but powerful concepts: topology and homotopy. Let's break down what they actually mean for how you learn.
Okay, first up, topology. I want you to picture all your knowledge like it's drawn on a giant rubber sheet. You can stretch it, you can bend it, you can twist it into all sorts of shapes, but here's the one rule: you can't tear it. Topology is basically the science of what stays the same, those fundamental connections, no matter how much you deform that sheet.
Right, so if topology is the rubber sheet itself, then homotopy, well, that's the action of stretching it. It's that smooth, continuous transformation from your old understanding to a new, more expanded one. In this way of thinking, homotopy is the process of learning.
So, why topology? Of all the math out there, why pick this one? Well, it turns out this approach has 4 huge advantages that make it pretty much perfect for modeling how we learn.
So what are these big advantages? Well, for one, it preserves the core of what you already know. It's also inspired by the brain itself. Plus, it's super efficient from a computational standpoint. And it's grounded in some really solid psychological principles. Let's go ahead and unpack each one.
First up, preserving that core structure. See, topology is all about what we call invariance, the stuff that doesn't change. This makes it a great model for how our foundational knowledge stays stable, even when we're piling on new information. The map stretches, but the major cities and highways, they all stay connected in the same way.
And get this isn't just some abstract mathematical idea. It's actually inspired by how our brains are wired. Literally. When we learn something new, our brain physically rewires itself, right? It creates new synaptic connections. But it does it in a way that keeps the existing pathways intact. Topology just gives us the language to describe this amazing biological process.
Okay, this is where the theory gets really practical. A lot of the older computational models for learning, well, they were incredibly slow and clunky. Think of them like trying to solve a ridiculously complex maze. But this topological approach, it's way more efficient. It's more like a rocket ship. It's fast, it's elegant, and it's actually suitable for the kinds of automated learning we want to build.
And this theory isn't just floating in a vacuum of abstract math, either. It's actually standing on the shoulders of giants. We're talking about foundational work from thinkers like Jean Piaget and D.O. Hebb. So it has these deep, credible roots in cognitive science and psychology.
All right, so this all sounds great in theory, but how does it actually work in the real world? Let's take a look at the actual tools that bring this whole idea to life.
So the framework really has 2 main parts. First, you've got something called VMS, that's the model, the structure that actually holds our knowledge map, and then you've got the algorithm that does all the heavy lifting, the learning part, and it has the absolutely epic name Gandels.
Okay, so let's pull back and look at the big picture here. What does all this really mean for our understanding of knowledge itself, for the very shape of knowledge? This quote from the research just nails it. Learning is characterized as a hemiotomy, a function of the deformation of a space in time. It's not a single aha moment. It's this continuous, flowing process of reshaping what you know over time. It's almost like a dance of transformation.
So if there's one thing to take away from all this, it's this. Learning isn't just about accumulating data. It's not just collecting facts. It's about the elegant, continuous, structure-preserving transformation of your entire mental world. You're adding new layers of understanding, sure, but you're doing it while keeping that core knowledge perfectly intact. And that leaves us with a pretty mind-bending question to chew on.
If all of our knowledge really does have a shape, just imagine what we could achieve if we learned how to consciously bend and reshape it ourselves. What new worlds of understanding could we possibly unlock?